All right, today's lesson is on rotations. By the end of this lesson, you should be able to identify when a rotation has occurred as opposed to some other transformation and know the mapping statements that find the coordinates of a new object or point after a rotation has been done. So first let's start about talking about what is a transformation and specifically what is a rotation. So when we think of transformations, many of you probably think of this. All right, but this is not what we mean by a transformation in math, although it certainly is a neat transformation. Okay, so now let's take a look at these cars going up and down and left and right on this intersection. In math, this type of transformation is called a translation. When we move something up or down or left and right, it's a translation, but we don't change its orientation. We don't spin it or change its size in any way. The type of transformation that we're going to be talking about today is called a rotation. So look at this figure on the right. Right in here, you can see that each of these triangles is being rotated about a point in that center triangle. All right, so a rotation in geometry basically just involves spinning an object about a point. And the point that we're going to be spinning objects about, in this lesson is the origin. So we say that the center of rotation is the origin. All right, so let's give you another visual example of what we mean by a rotation. So take a look here. This demonstration here is showing you that if you have physical graph paper, you can literally just turn the graph paper, in this case 90 degrees, and then write down the new coordinates of the point. If you wanted to perform a 180-degree rotation, you would simply turn your graph paper by 180 degrees, and then you could label the coordinate of your new point. So here's that same point, 1, 2, and now we're going to go ahead and perform a 270-degree rotation. Notice how this point is just spinning about that origin. That's our center of rotation there. It'd be like a tire, it'd be like the center of the tire would be the center of rotation. And then finally here we can see that if we perform a 360-degree rotation, we end up exactly back where we started, right? Because there's 360 degrees in a circle. So as we rotate a point about the quadrants, right, you can think about it as just kind of spinning the graph paper underneath it, right? And each quadrant is 90 degrees. There's a 90-degree turn, a 180-degree turn gets us through quadrant 2, a 270-degree turn gets us through quadrant 3, and then a 360-degree spin would be back where we started. Now, when we're talking about rotations, a positive degree measure indicates a rotation in the counterclockwise direction. All right, so if a problem just says perform a 90-degree rotation, it means do it in the counterclockwise direction. Negative degree measures would indicate a rotation in the clockwise direction. Otherwise, they'll just state rotate it counterclockwise or rotate it clockwise. All right, so let's talk about a 90-degree rotation about the origin. All right, so when performing a 90-degree rotation, remember that does mean counterclockwise unless I specify clockwise. When performing a 90-degree rotation, point A will be mapped to its new location, A prime. So that little tick mark above the A, we call that A prime. Where we started from, the original point, in this case point A, is called the pre-image. And then after we do the transformation, in this case it's going to be a rotation, the new point that we get, which is indicated with that tick mark, remember, which we call A prime, that's called the image. All right, so the rule to perform a 90-degree rotation, right, is that we take the x and y coordinates and we switch them and then make that y coordinate, the original y coordinate, negative. So take a look at the point A here that originally had coordinates 2, 1. According to this rule here, I switch the points. Okay, so I would go ahead and switch them. I like to do it myself one step at a time. So here's my point 2, 1. Okay, switch the x and the y. Okay, so now it'd be 1, 2. Oh, and then make that first one negative. Okay, so negative 1, 2. And there's the coordinate of A prime. This diagram here is just showing you that a 90-degree rotation was performed, that we actually moved a 90 degrees in the counterclockwise direction. All right, so you try. Look at the coordinates of this point on this graph and perform a 90-degree rotation counterclockwise. Pause the video and take a moment to work out the new coordinates. All right, so here's the rule again. It says that we should switch the x and y, right, and then make the new x coordinate negative of what it was before. So the way that I interpret this is, okay, well, here's 4, 1, there's my point. I should switch those coordinates, switch them. Okay, so I'll make it 1, 4, and then make that first one right there, make that negative. Oh, so negative 1, 4. So I can go ahead and plot that. Here's negative 1, 4 on the graph. Right, and we can see that that is a 90-degree rotation counterclockwise. Right, we shifted it. Imagine turning that graph paper again. Right, another point to make when we're rotating points, right, is that the distance from the origin, right, the center of rotation, that distance from the center of rotation does not change. So this distance from the origin to 0.41 is going to be the same distance as it is now, right, from the origin, from at point negative 1, 4. All right, so we did not change, we didn't move it up and down or left and right, we just simply rotated it. All right, so let's talk about a 180-degree rotation about the origin. All right, so this should say when performing a 180-degree rotation, excuse me, counterclockwise. Remember, it's always counterclockwise unless we specify otherwise. Point A will be mapped to its new location, A prime, using the following rule. So this one's particularly easy. It just says you take the point and you change both the signs. So leave the x and the y where they are and change the signs. And so notice how point A, that's called our image, sorry, excuse me, our pre-image is at the location 2, 1. After we perform a 180-degree rotation, it ends at its new location, negative 2, negative 1. So notice how we just change the signs on the x and the y coordinates. This doesn't mean that the x and y are always negative when we perform that rotation. It means they're the opposite of what they were before. So for example, if we had a point A that happened to be at, say, negative 3, 1, right, then if I did a 180-degree rotation, the new point A prime, we would just change the signs on both of these. So now it would be at 3, negative 1. All right. All right, so now you practice. Let's take that same point that we used an example for the 90-degree rotation, and let's rotate that point this time 180 degrees. All right, so the location of the new point you should have had is you keep the coordinates the same and you change their signs. So you should have had at negative 4, negative 1. And you can see negative 4, negative 1 is here. Notice the distance from the origin hasn't changed. And we've performed a 180-degree rotation. Part of the, and I'll talk about that in a second after I finish this last one with these points. We'll get back to some of your discussion questions. But let's do the last type of rotation we're going to talk about, which is a 270-degree rotation. We don't need to discuss rules for a 360-degree rotation, right? Because that actually doesn't change the location of the point. You'd end up back where you started. So that's why we only have rules for 90, 180, and 270. So in this course, you're never going to be rotating anything other than using those particular degrees at 90-degree intervals. Although you certainly can rotate something 55 degrees and 60 degrees. And then the way that you would come up with a new image there is beyond the scope of this class right now. All right, so let's talk about our last rule, right, when we perform a 270-degree rotation. So we can see here that we go ahead this time and we switch the X and Y coordinates again. And then we make the second, we make the Y coordinate now negative in our image. So take a look at A, right? It's the pre-image. It's at that point 2, 1 again. Now we're going to do the 270-degree rotation. So it was in quadrant 1, right? Now we go through quadrant 2, quadrant 3. It ends up in quadrant 4. And according to this rule here, we switch the coordinates. Okay, so, we switch them. All right, so I'd have 1, 2, and then I should make that second one the opposite sign. Okay, so -2. And that's exactly what we end up with there. Notice that a 270-degree rotation counterclockwise would be exactly the same thing as a 90-degree rotation clockwise. And so let's practice rotating a point. Let's rotate this point 270 degrees. Again, after a 270-degree rotation. All right, so using the rule here, it says I should take my point, I should switch the coordinates. Okay, so I switch them. So 1 first, then the 4. Then make that second one negative. Okay, so -4. So you can just do that then and then plot our new point. Here's 1, -4. And that does seem logical. If I rotated it through the 3 quadrants here, I would first rotate 90 degrees counterclockwise and I'd end up here. Then I would rotate another 90 so to get to 180 and I'd end up right down here. And then if I finally do the 270, rotated another 90 degrees, we end up with our 270-degree rotation. All right, so how to identify a rotation? All right, so when rotating line segments or other geometric figures, the shape and size of the object does not change. All right, so that's the first thing you're looking for, that the shape and size didn't change. In math, we have a special name for that type of transformation. We call it an isometric transformation. Okay, so that means that the length of line segments aren't going to change. It means all angle measures in, say, a triangle or any other polygon are not going to change. They're going to stay the same. The next thing that you're looking for when you're identifying a rotation, right, is that the orientation of the object will not change as it is rotated through the quadrants, right? So the orientation of the object will change when you're doing a rotation. But if you were doing say, a translation, then it wouldn't change, right? The orientation wouldn't change of the object. It would just be moving it up, down, left, or right. So that's another key feature that you're looking for when you're trying to identify if a rotation was done. If its orientation has changed, then I suspect a rotation. You have some discussion questions about how can you identify if a rotation was done when you're moving a point. And that's kind of a tricky question. Let's go back one slide and let's take a look at, say, this point. And say this point ended up here. You see that this is the result in this case of a 270-degree rotation. But it also could be the result of me shifting the point down and then left. Right? So it could also be the fact that I translated this point to its new location. And when we're dealing with points, there's really no way for me to tell the difference between a rotation and a translation. All right, but when we're dealing with objects like line segments and triangles and polygons, then I can tell. I can tell by looking at the orientation of the figure. All right, so that's why that's important. All right, so let's practice identifying some of these rotations. Let's look at each of these figures down here, all 6 of them, and let's identify the transformation that was used in each. All right, so this figure in the upper left-hand corner. To get from the red line to the blue line, does it look like we performed a rotation? I'm looking at this. These lines look parallel. So maybe a 180-degree rotation could have been done. But if I had done that, it would have been way over here instead of all in the first quadrant, right? It would have ended up way back here in the third quadrant. So in this case, we can tell that what was done was a translation. Right? So in this first figure is a translation. It looks like to move one point, the red point to this blue point, we went up one and to the left two. And every point was translated in a similar manner. Right? We can tell that no, the orientation stayed the same. Right? We didn't rotate it any. How about the second figure here in the middle? So now we're kind of looking at, in this case again, two line segments. Notice that here we're drawing the picture where these little dashed lines represent the distance from the point to the origin, which is our center of rotation. And yeah, we can see that in this case, a rotation was in fact performed. Notice how the line here did change its orientation. Here it's kind of in this direction. Now it's up and down. So that's my first clue that maybe a rotation happened. And then the next thing I would check, right, is that the didn't change its length. That this length is still the same length as that length. All right, and we know that in this case because they went ahead and labeled our new points for us, so we can see that the distance from the origin to those points did not change in each case. Let's take a look at the third figure. So was a rotation done here? All right, so if that was a rotation, let's see if I get point B here to point B prime. Maybe I rotated it. Maybe I went this way 180 degrees. Let's see if I rotated it though. Maybe I went this way, for example, and then I ended up with this figure. But let's see if that happens, right? Then wouldn't this B prime be down here? And A would be up there. But since A and B did not change their orientation from the image and the pre-image, and they're both the same distance from, it looks like in this case, the y-axis, you can see that B is 3 away from the y-axis, and B prime is 3 away from the y-axis, and A is 5 away from the y-axis, and A prime is 5 away from the y-axis. So in this case, it looks like a reflection was done. They're mirror images of each other. It's like if we took this and folded it across that line, then they would match right up on top of each other. Notice if we had rotated this line segment to get to this line segment, then the orientation of where the B's are would change. Like I'm saying, this one would be down here, right? The B prime would end up down here, not up there. All right, so let's look at the fourth image here. Again, we can see it's another type of reflection. Notice how it didn't rotate through the quadrant. In this case, C, maybe C rotated and we got to C prime, but then that would have put A prime down here where the B prime is, right? If this whole triangle rotated. But we can see that's not what happened. In fact, it looks like it was just folded over this line at x equals 5 in this case. So in this case, that C is 1, 2, 3, 4 away from that line of reflection. And C prime is 1, 2, 3, 4 away from that line of reflection. So that's kind of my cue that it was folded over some line. We don't only have vertical reflections, over a vertical line. We can do it over a horizontal line too. And then you would still see that same mirror image type of effect. Let's take a look at this next image. So is the blue triangle a rotation of the red triangle? Yeah, no, it's not, right? In fact, this is another translation. Notice that the orientation stayed the same. If it were a rotation, we'd expect that orientation to change. But it didn't. A stayed in its same relative position, and B. All we did is move this triangle up and over. And then finally, the last figure is a rotation. So we can see to get from triangle DEF to triangle DEF prime, right, that we would have had to rotate it one 190 degree, 290 degrees, 390-degree turns, or 270 degrees in the counterclockwise direction, which is the same as a 90-degree rotation in the clockwise direction. So notice the orientation changed, but the shape and size did not. All the angle measures were maintained. All the lengths of each line segment were maintained. And that's what we mean by an isometric transformation. The size and shape of these things don't change. All right, so let's practice rotating some line segments. Okay, so take a look at this diagram here. Which segment is a 90-degree rotation clockwise this time? See, we had to specify clockwise of segment AB. And then let's go ahead and see if we can write the mapping statement for that rotation. All right, so if I'm going clockwise, right, I'm going in this direction. We're moving like a clock. So that means if I'm moving segment A, B here in the clockwise direction, I'm moving it in this direction around our coordinate plane. Then we're going to move it 190-degree turn. So right now, if it's in quadrant 1, and I'm going to move it clockwise, it's going to end up in quadrant 4, which is down here. Right, so if any of these are a rotation of that segment, it would have to be line FE, segment AE, excuse me. Segment FE, and this is how we write it in geometry with a little line above it. All right, the next thing I would check just to make sure that it really was a rotation, right, is that the length was the same. And we got to make sure that we didn't change the size of this. My eyeball tells me that it looks like the same length. One way to kind of look at it is to find, look at this, to get from point A to B, I had to go 2 down and right 3. So if we have the same kind of relationship between these 2 points, then I can kind of say those distances are the same. Otherwise, you're going to have to use the distance formula. But here I can see that the difference in vertical direction here is 3 and the horizontal 2. So it really is the same figure. Think of that. See how I kind of drew that triangle? It's the exact same size and shape. So I know those are the same length. All right, so we went ahead and rotated this one 90 degrees. And it looks like that A would match up with E, right? And B would have matched up with F. Let me clean this up a little bit for you. Let's go ahead and let's write the mapping statement then. So the easiest way for me to do that is to start out where point A was. So our original point A is, let's write its coordinates down, 1, 3. And then let's see where it ended up. All right, so after we did the 90-degree rotation, point A, right, remember this is the same as a 270-degree rotation, right? So if you imagine that point A would be here, then here, then here, then up here where the E is now. All right, so now the new coordinates of this point here are at 3, -1. So I'm going to go ahead and write that down. So 0.13 got rotated to its new location, 3, -1. So let's take a look at what happened here to the coordinates points. So if I had an X and a Y coordinate, what did we do to get to our new coordinate? So let's see, it looks like I switched them, right? The 1 and the 3 are switched here. Okay, so let's do that. Let's go ahead and switch. So the Y will become X and the X will become Y like this. But then that's not it, right? Then we went ahead and made that one, the second one here, negative. So the X coordinate here that was a positive one now became the new Y coordinate with a negative sign in it. So I'm going to go ahead and make that second coordinate negative. So that would be the mapping statement. And if you'll notice, right, if you pull out your notes from what we were just doing, that is the exact same mapping statement as a 270-degree rotation in the counterclockwise direction. Now let's try this one. Is segment CD a 180-degree rotation of segment AB, and how do you know? All right, so I go ahead, I look back at my notes if we need to look at it. We can see that for a 180-degree rotation, this is our mapping statement. You know, you take it to get from one point to another, we would just make the signs opposite. All right, so that's the mapping statement for a 180-degree rotation. So let's see if CD really is a rotation of AB, then let's go ahead and take segment AB and let's perform a 180-degree rotation and see if we end up with line CD. So right now, they look like they're the same size to me. And in fact, if we went ahead and counted that horizontal change and vertical change from one point to the other, they would be the same in both lines. And we'd have that same ratio. So they are the same length. You could also use the distance formula to calculate those lengths, right? But they happen to be the same. So now we just make sure that the points would end up where they are. You can also just kind of visualize, you know, I can't do it as easily here if you had graph paper in front of you by hand. But as what you would imagine doing is just spinning this 180 degrees at one time, two time, and try to imagine where the new points end up. All right. In this case right now, since I can't do that on my screen, I'm going to go ahead and use the mapping statement to plot our new points. So it's just saying I should change the signs. So where would point B end up? Well, if B right now is at the point 1, 3, then after I perform my 180-degree rotation, I should just change the signs on my X and Y. It would end up at -1, -3. All right, so I'm going to go ahead and plot that point. Here's -1, -3 right here. All right, so that would be B prime. That'd be where should end up. Notice it's not either the point C or D. So already I know that this was not a 180-degree rotation. But just to show you what it would look like if we completed it, let's go ahead and do the 180-degree rotation on the endpoint A here. So right now A is at the point -1, -2. And when I perform a 180-degree rotation, remember we just changed the signs. Remember, this doesn't mean that the X and Y are always negative when we perform that rotation. It means they're the opposite sign. So right now it's at -1, -2. So it's going to end up at +1, +2. All right, so that would be this point right here. And that would be where A prime would end up. And then we could go ahead and connect those 2 points with our line segment. And that's where, if we in fact performed a 180-degree rotation on line segment AB, this is where it would end up, not where CD is. Another thing you might have realized is that if I have a line segment like this and I perform a 180-degree rotation, I end up with those line segments being parallel to each other. They end up being parallel. And you would notice that too if we went ahead and mapped CD the same way and did a 180-degree rotation on it, we'd get a point here and here, and then we'd see that it was parallel to line CD. Okay, so that's the same idea here as mapping triangles. In fact, when you have a figure like a triangle or a polygon, it's almost easier to visualize the rotation, right, than if you have just a line. And with a point, it's really impossible to visualize it, right, because it could have also been a translation. All right, but here it's really easy to see if the figure changed orientation or not. So the question here is, which image is a rotation of B counterclockwise 90 degrees? All right, so if we took B and we rotated it counterclockwise, that's in this direction, 90 degrees, right, it would end up right there where A was. So it'd be where triangle A is. Now, Maria claims that this rotation in a clockwise direction, she claims that a rotation clockwise 90 degrees would produce the following mapping statement. And is she correct? Well, there's a few different ways to approach that. So now what Maria is saying that, hey, if I rotated this clockwise, that means now in this direction, this would be the new mapping statement. So one way to do it would be to pick a couple of corresponding points and see if that indeed was the mapping statement. Another way to look at it is to know that a 90-degree clockwise rotation is equal to a 270-degree counterclockwise rotation. So I'll put CC for counterclockwise. And we already know the mapping statement for that. We know that XY should be mapped to Y negative X. Now, that's not what Maria said, though. Right? Maria should have put the negative on the X. So already I'm thinking Maria's wrong. But let's just to check, just to double check. All right, I can go ahead and we can label a point and then label its corresponding point because we can see that triangle C is in fact a 90-degree rotation of triangle B in the clockwise direction. So let's see if her mapping statement holds up by checking a point. All right, so I like to look at that right angle, that corner point there. It has to match up with this one, so that's pretty easy to pick out. So the coordinate here was 1, 6. Right now, according to Maria's argument here, we should switch them. Okay, that would be 6 and a 1, and then make that first one negative. So the new point should end up at negative 6, 1. All right, well, let's see. The negative 6, 1 would be right here, not where it actually is in the picture. So already we know this cannot be correct. Let's go ahead and see where this point correctly is mapped using a 90-degree clockwise rotation. Well, the new point ends up to be in fact at the x is 6 and the y coordinate is negative 1. So now notice that it is in fact what we wrote for a 270-degree counterclockwise rotation. Because look, it's saying I should switch the x and y. Okay, so we switched them. So I put the 6 first, then the 1, then make the second one negative. Okay, and that's exactly what we did. We switched them and then made the second one negative. All right, so now your turn. Go ahead and pause the video and tell me if you can answer which image is a rotation of triangle A, which 180 degrees counterclockwise. All right, so the answer is, so which one's 180 degrees of triangle A? There's 90 degrees, 180. Right, so that would be triangle C. Is triangle C a rotation then of triangle B? And what would be the mapping statement? Well, from the last slide, this should be very familiar, right? So triangle C is in fact a rotation of triangle B. And in the positive direction or the counterclockwise direction, it's a 270-degree rotation. And the mapping statement for a 270-degree counterclockwise rotation, remember, typically I could just say 270 degrees and it's implied counterclockwise. All right, negative degrees imply clockwise, or they'll tell you. Right, just to make it super clear, I think in most of your checkpoints and your exams, it actually will use the word counterclockwise or clockwise, just to specify to you. All right, so in this case, the mapping statement is that any point xy gets mapped to, remember what we do, we switch the x and the y, and we make the second one negative. All right, so you don't really have to memorize all these rules. I would have them written down somewhere just so that you can refer back to them. All right, and then go ahead and perform the rotations using those rules. Another way, if you actually have the graph paper, to actually be turning it. 90, 180, 270 degrees and flipping it around like that is a real nice way to do it because then you don't have to memorize any kind of rules, right? You just look at and see where the new points end up. Remember that you can do that as long as the center of rotation is the origin. And for all your problems, that's going to be at the origin. Okay, so our final practice there. Let's go ahead and rotate this triangle 180 degrees counterclockwise and draw the new triangle. So the very first thing that I would do, right, is look back in my notes and find that mapping statement. Find how I perform a 180-degree rotation. All right, so for any x, y point, I'm looking it up now in my notes. It says I just switch, I just change the signs. And so I leave the x, y same, I just change the signs. All right, so let's go ahead and let's plot point A. All right, so remember, we refer to this image, the original image, right, as the pre-image. Okay, so pre-image, point A, that point is at 1, 2. All right, so then after I perform a 180-degree rotation, the image, the new point, which we call A prime, is going to be at, oh, just change the signs. Okay, so -1, -2. Okay, let's go ahead and plot that. Here's -1, -2. All right, and that's going to be point A prime. All right, so let's do the same for point B. Point B is currently at location 4, 5. All right, so B prime, hey, just switch the signs. Easy enough then. -4, -5. Done. All right, so that point now is at -4, -5. And there's our point B prime. Finally, point C in the pre-image is at point location 6, 3. All right, and after I apply the 180-degree rotation, the mapping statement tells me just change the signs on the x and y, so we'll end up at -6, -3. I'll go ahead and plot that point. All right, here's the point -6 back here on the x down to -3 right there. All right, and that is our location, that is a C prime. All right, now I can go ahead and connect and draw my triangle. There, and you can kind of visualize that, right? The shape didn't change, the size didn't change, the orientation did change. You can kind of see that I would, if I rotated it 90 degrees, I'd end up here in the second quadrant. And then another 90-degree rotation for a total of 180 would have put me here in the third quadrant. And it does look like I just spin it 180 degrees. So it takes a certain amount of visualization as well. So in summary, right, these are the 3 rules that you should have written down, your mapping statements. This is the one for a 90-degree rotation, a 180-degree rotation, and a 270-degree rotation. All right, so make sure now you go back to the course announcements and answer the questions.